Hello and welcome to lecture 48. We are discussing about design of low speed contra-rotating fan. So in last lecture we were discussing about design of low speed contra-rotating fan for different aerodynamic loading. So if we look at here, this is what is representing when we are considering our aerodynamic loading, say 1200 for rotor 1 and 800 Pascal, that's what is for rotor 2. We also have discussed about when we are changing our aerodynamic loading, that's what is 1100 Pascal for rotor 1 and 900 Pascal for rotor 2. Here in this case, if we look at by changing our aerodynamic loading for rotor 1, say 1200 and 1100 Pascal, we can clearly see how my shape of the blade, that's what is changing all the way from hub towards, say, our tip region. Okay, and since we are doing our design for tip loaded configuration, in order to have, say, reasonable degree of reaction near the hub region, we are having this curvature that we can see. Say for rotor 1, for 1200 Pascal, we will be having, say, larger turning of flow near the tip region. If you are considering for, say, rotor 2, not much variation, that's what we can see. But at the same time, because of change of aerodynamic loading near the tip region for rotor 1, accordingly the tip loading, that's what will be changing for rotor 2. Now this is what all we were discussing about the fundamental concept or fundamental method for the design. Let's discuss today for the next step. Say we will be doing our design for this contra-rotating fan using second concept, that's what is, say, free vortex concept. We can understand, say we have discussed the design of, say, axial flow compressor with different design methods. Similar kind of concept can be adopted for design of contra-rotating fan. But for the sake of brevity, we will be discussing here one more method for the design, that's what is, say, free vortex design method. So for free vortex design method, the design procedure, that's what will be similar to what all we have discussed for fundamental method till midsection. So we will not be repeating those calculations what we have done for the midsection. Now we know when we are talking about, say, low speed configuration, we are doing our calculation for midsection at 50% of span. Do not forget both the logics, that's what is applicable for rotor 1 as well as for rotor 2. Here in this case, once we have done our calculation at the midsection, then we will be adopting the low concept, or we can say world distribution concept. That's what method we will be opting for. Here in this case, we will be using, say, free vortex design concept, for which we will be taking CW into R equal to constant for rotor 1. Similarly, here for the design of rotor 2, we are making assumption that the flow which is coming out from rotor 1 with absolute velocity of C2, the same flow or same absolute velocity with which flow will be entering in my rotor 2. That means if we are considering our absolute flow angle at the exit of rotor 1, say alpha 2, that's what will be equal to alpha 3. This is what we are making assumption in order to simplify our design process. And later on we will be discussing, and we know, like, we have adopted this method and with which we have done our design, that's what is working absolutely fine with. Here in this case, if we consider now for rotor 2, we have discussed the flow which is coming out from rotor 1, that's what will be having some whirl component, say CW2. Now this whirl component, that's what will be having the direction, that's what is opposite to the direction of the rotation. So we can say this whirl component, that's what will be getting added up. We will see all this calculation when we move ahead with. So let's check with, so this is what we already have done calculation at the midsection for the rotor 1. So here in this case we have taken our pressure rise as 1200 Pascal. So we will be using this free vortex design concept for 1200 Pascal of rotor 1 and 800 Pascal for rotor 2. So if we are opting for that, we have done our calculation for the constant. We can say for free vortex, we are taking CW at midsection and my radius at the midsection. The product of that, that's what is coming to be constant, and that's what we are calculating as 4.84. Now, this is what is a concept, that's what we have discussed for our state design. Same concept we can use for our contra-rotating fan design. Here in this case, at the midsection, as we have discussed, we have done our calculation for CW into R equal to constant. Now, we will be using this free vortex concept, say above the midsection towards the tip region and below the midsection towards the hub region, where we will be putting our CW into R equal to constant. We know here in this case my constant, that's what will remain same. My radius, that's what will be changing. Now, since my radius is changing, that's the reason why my whirl component, that's what will be changing. So my whirl component, that's what will be changing all the way from hub to tip. Okay, and based on that, we are doing all our calculations. So if we recall, basically by calculating our velocity components, say peripheral speed, my axial velocity, my tangential velocity, absolute velocity and relative velocity, we will be having the distribution of flow angle along the span. Okay, so let's move ahead with the calculation at other stations. So we will be doing our calculation at the hub. So what we know from our free vortex concept, we can say CW into R equal to constant, that's what is coming, say 4.84. Now at any radial station, we can put CW2 at any radial station, that's what is constant by particular station radius. So here in this case, CW2 at hub we can calculate by using this radius as well as by concept. So it's coming, say 71.65 meter per second. Now since we know what is our CW2, we can calculate what will be our flow angles. So we will be calculating our exit blade angle, that's what is say beta 2, that is given by, say based on our velocity triangle, we can say C1, it is nothing but U minus CW2 divided by CA, and that's what is coming minus 50.92. Same way, based on velocity triangle, we can do our calculation for beta 1, and that's what is coming 20.90. Be careful when we are doing our calculation at different station. Accordingly, you need to modify your velocity triangle. Here at the hub station, we are having velocity triangle, that's what is coming to be different. Okay. Now, say once we have done our calculation for these blade angles, we are interested in calculating our de Horler's number, and for that we are looking for calculation of our relative velocity. Now this relative velocity at the entry based on sine rule, that's what is coming as say 47.52 meter per second. Same way for exit velocity triangle, we can say my relative velocity at the exit near the hub region, that's what is coming 70.45 meter per second. Okay. Same way we can do our calculation for absolute velocity component also. So my C2, that's what is coming 84.28 meter per second. Now we know our de Horler's factor, that's what we are defining as a ratio of velocity, a relative velocity ratio, that is nothing but V2 by V1. So here this is what is coming to be 1.48. Okay, this is what is coming slightly on the higher side. We will see as compared to our say fundamental method, this number is coming on the higher side. Now after doing this calculation, we will be checking with what will be our diffusion factor for rotor 1, and in order to do that calculation, we are looking for say Carter's parameter or slope factor. That slope factor which is given by this equation, it is 0.23 2a by c square plus 0.1 90 minus beta 2 divided by 50. Now if we will be putting the numbers, it says my m, that's what is coming 0.511. Now once we know this m parameter, we can check with the calculation of our solidity. Now for the calculation of the solidity, we can say that is nothing but it is given by 2 pi r by z. So we can say the radius at the hub, it is known to us. As we have done calculation for the number of blades to be 19 for say rotor 1, the same number of blades we will be putting. That's what will be helping us for say comparing our results. Okay. So if we are taking my number of blades for rotor 1 to be 19, we can say my pitch is coming 0.022. Okay. And based on that, since we already know our chord, so we can calculate our solidity near the hub region, and that's what is coming 2.017. Now once this solidity is known to us, we know we can calculate our diffusion factor. Now diffusion factor correlation, that's what is in sense of beta 1, beta 2 and solidity. We know what is my beta 1 and beta 2 at the hub station. Same way, be careful, this solidity, that solidity is not remaining constant throughout my span, because solidity, that's what is a function of my radius, and that's the reason why solidity, that's what will be varying all the way from hub to tip region. Okay, so if we are putting that number, this diffusion factor, that's what is coming minus 0.11. So this is what is little disappointing in that sense. But you know, like for free vortex concept, we are not having we are not having control for these numbers. So whatever numbers, that's what is coming, we will be taking care of at the initial stage, and maybe as and when required, we will be modifying these numbers. Okay, so do not get confused with diffusion factor, that's what is coming to be negative in this case. Okay, now you know, like once we have done our this calculation, so we can go with say calculating our cascade parameters. Now as we have discussed earlier, say we will be assuming our incidence angle at the hub to be positive 2 degree. So we will be taking that as positive 2. We can calculate our camber angle at the hub, that's what is nothing but delta beta minus incidence divided by 1 minus m divided by sigma. Okay, and if we are putting that number, my camber angle is also coming to be large. This is what is coming 109.07. You can understand, like when we will be discussing all our results, we will be realizing what all are the limitations or what all are the challenges when we are opting with free vortex design concept. And that's the reason why intentionally initial calculation we are showing for the hub station. Okay, now once we know what is our camber angle, based on say by Carter's correlation, we can calculate deviation angle, that is nothing but m into theta divided by sigma, and that's what is coming 39.24 degree. Same way we can calculate our blade setting angle, or we can say stagger angle, that's what is in sense of beta minus incidence minus theta by 2, and that's what is coming minus 35.63 degree. Okay, so this all are the calculations for my cascade parameters or airfoil parameters or blade parameters at particular station, that's what is at the hub. Now what we are looking for is we are also looking for the calculation what is happening near the tip region. So in line to what all we have discussed at the hub station, same logic, that's what is applicable here. Now we will be applying say our free vortex design concept near the tip region. So we can say my CW2 at the tip, that's nothing but it is constant divided by RT. Okay, now if we are putting this as say CW2, it is coming 23.88 meter per second. We can do our calculation for the blade angles beta 1 and beta 2 at the tip station. Okay, here in this case we will be calculating beta 2, that's what is coming 31.31 degree. My beta 1 at the tip, that's what is coming 48.82 degree. And my alpha 2, that's what is coming 28.27. So this all what we say, that's what is based on our velocity triangle and based on trigonometry. This is what all we have discussed earlier also. So without taking much time, let's move ahead with the calculation for the relative velocity ratio near the tip station. So here this is what we can say. We are having my inlet relative velocity as 67.61 meter per second, my outlet relative velocity as say 51.97, and absolute velocity is coming 50.41 meter per second. Okay. Now when we are taking this ratio, that's what is coming as a 0.76. Okay, and as we know that need to be greater than 0.72, and that's what is happening here. Okay. Now in order to calculate our diffusion factor, the M parameter, that's what has been calculated near the tip station, and that's what is coming 0.347. Now once this M parameter is known to us, we can do our calculation for the solidity and the diffusion factor. Now for solidity, as we have discussed, we have our number of blades to be 19 for rotor 1. Now we will be putting say 2 pi r into my tip radius as a 0.2025, and 19 number of blades, that's what is giving pitch to be 0.066. Okay, and the solidity is coming 0.672. Okay. Now based on this solidity and my blade angles beta 1 and beta 2 near the tip station, we are able to calculate the diffusion factor at the tip, and that's what is coming 0.489. So like this is what will give idea how my say de Euler's factor, how my diffusion factor, that's what is happening, or that's what is coming near the tip station. In order to have the parameters for the generation of blade, we are looking for the blade angles, we are looking for say airfoil angles, that's what we are defining as a camber angle, stagger angle, and say deviation angle, that's what we are calculating. As we have discussed here, we are assuming our incidence angle near the tip region to be -2 degree. When we say this is what is a -2 degree, we can calculate our camber angle, and that camber angle, that's what is coming 33.98. We are having our deviation angle, that's what is coming to be 14.4, and the stagger angle is coming 33.90. Now as we have discussed earlier, for the calculation for stage, in line to that we will be having all these parameters, that's what is coming. Okay, combinedly we can say hub, mid and tip station. If we make the observation, my CW2, that's what is coming 35.82, and here my delta beta near the hub station, that's what is coming to be large, that's what is coming say 71.83. Now diffusion factor variation, we can say it is -0.11 to 0.49, and this is what is a variation of my delta beta. Now this is what all we are discussing about say free vortex design concept at 3 different stations, hub, mid and tip station. Now in order to understand, we will be dividing our whole span into say number of stations. Say for the sake of simplicity, we have divided our whole span into 11 stations. So you can see this is what is representing my different radial locations. And as we have discussed, we are having our CW into R, that's what is coming to be constant. Okay, and based on that we are calculating what will be my CW2. Now once the CW2 is known to us, we can do calculation for different flow angles. Okay, and that's what is giving me my delta beta to be varying from say 71.83 to 17 degree. So this is what is large delta beta, that's what we are getting for the free vortex concept for rotor 1. And my diffusion factor near the hub, that's coming to be say minus 0.11. Maybe if required, we need to do certain modification in sense of loading such that we will be getting this number to be positive. Okay, and this camber angle also is coming to be very large in the case of free vortex concept for rotor 1. Now if you look at here, this is what is representing how my beta 1 and beta 2, that's what is varying along my say span. So this is what is representing the span. If you look at here, for the free vortex concept and rotor 1 design, we are having larger delta beta, that's what is coming here near the hub region, and near the tip region this angle, that's what is getting reduced. Okay, so this is what is representing. So near the hub region we will be having this delta beta, that's what is coming around 70 degree, and near the tip region that's what is coming around 21 degree. Since we are having our alpha 1, that's what is axial entry, and this is what is representing my alpha 2, and this is what is representing my diffusion factor for the rotor 1 and de Holler's factor for rotor 1. Okay, now let's try to compare with our fundamental designs. Okay, here in this case, if we are observing carefully, say my beta 1, that's what is same for both the design cases, for fundamental approach as well as for free vortex approach. But here in this case, my beta 2, if we are looking at, then my beta 2, that's what is coming to be larger for free vortex concept. So here my beta 2, that's what is coming to be larger. Okay, so delta beta is coming to be higher. Now if we compare our fundamental design method, it says my delta beta is, it is nearly half in the region. And if we are comparing our delta beta for fundamental design approach, it is not giving very high twist to rotor 1 blade. But we are considering, if we are considering our free vortex concept, for that we will be having our delta beta to be coming as large from hub to tip. Okay. Now this is what we were discussing about. Same way, if we are comparing our de Holler's factor, that is also coming in a great control when we are talking about the fundamental design approach. When we are talking about the diffusion factor, it shows a smooth diffusion, that's what will be going to happen. Now we are not criticizing any design method. Okay, whatever design method we will be adopting for design and development of rotors, that's what is absolutely fine if it is working as per the expectations. So it is designer's choice to opt for which kind of method or what rotor and how the design method or world distribution he will be opting for. If it is giving what results are expected or what performance are expected, and if it is working absolutely fine, that's what is the design approach. Okay, so do not misunderstand in sense of free design, say free vortex design concept and fundamental design method concept. Okay, now we have discussed about the corrected flow angles. So here also, in order to have similar discussion in sense of my deviation angle, we have discussed what all we will be getting using the computational method or computational analysis. Accordingly, we need to modify our deviation angle. So let's assume the variation of say deviation angle, we are taking that to be 4 degree. Okay, if we are assuming that to be 4 degree, accordingly we will be having corrected camber and corrected stagger. And as we discussed, this corrected camber and corrected stagger angle, that's what will be used for making of the blades. Okay, so if we look at here, this is what is representing, say by having, this is what is representing my free vortex design concept. So we can see we are having highly twisted blade, that's what is coming for rotor 1. And if we are comparing, this is what is our fundamental design method for say 1200 Pascal and 800 Pascal distribution, my blade twist is coming to be lower. Okay, Now, same design concept or same methodology we can opt for rotor 2. So, here in this case, we need to be very careful when we are doing our design for contra-rotating fan, as we made the statement earlier and as we have discussed at the initial stage also, we are assuming our absolute velocity, say my C2 and C3 to be same and my alpha 2 and alpha 3 to be same. If we are considering that as a case, we will be having our CW2 and CW3, that's what will be coming to be same. Now my whirl component at the exit, that's what is important when we are doing our design for free vortex concept. So we will be doing our calculation for CW4 into R equal to constant, and that method, that's what we will be opting for designing or calculating different flow parameters, different flow angles, velocity components at different stations. Okay. Now, same in line to what all we have discussed for say design, here we will be calculating the flow parameters at hub station. So, as we have discussed here in this case, we are taking my C2, that's what is equal to C3, my alpha 2 equal to alpha 3, and that's the reason my CW2 equal to minus CW3. Be careful about that part. When we are considering that as a case, we will be able to calculate what is our beta 3. Here in this case, this is what is U minus CW3, but the CW3, that's what is nothing but it is minus CW2, and that's the reason why my beta 3 is coming to be 63.38 degree. The same logic we have discussed for our fundamental design approach also. So do not get confused why this sign is coming as a negative. Okay. Now we will be opting for our free vortex design concept at the exit of rotor 2. So we will be putting CW into R equal to constant, since my CW4, that's what we have calculated at the mid station, and based on that my constant is coming minus 1.27. So if we will be using that, we are able to calculate what will be our blade angles beta 3 and beta 4 for rotor 2. Okay. So here in this case, my beta 4, that's what is coming 38.83, and my delta beta, that's what is coming say 24.54. Okay. Now in line to that, we will be able to calculate what will be our flow angles, say alpha 4. We can calculate what will be our say relative velocity components. So my V3 and V4 based on our velocity triangle, we can calculate. Once we are calculating this, this is what will be helpful to us in order to calculate the de-Holler's factor. That's what is coming 0.58. Okay. Now in order to calculate our diffusion factor, we will be doing our calculation for slope factor. That's what is coming 0.28 for the hub, and diffusion factor, that's what is coming to be 0.57. Now this is nothing but it's a repetition of calculation. We need to be very careful when we are doing our calculation. We need to select the radius as per the station. So it is preferred that as and when you are doing your calculation, you just carry forward the data what all, that's what is available here. So here you can see I'm putting my RH, I'm putting my chord, I'm putting my beta 2, beta 3, beta 4. So that's what will be helping us in order to avoid the mistakes that will be happening when we are doing pen paper calculation. Anyway, this all calculation we will be cross verifying using the Excel sheet. So there is no problem at all for this kind of design calculations. Okay. Now based on that, we can do our calculation for say angle theta, deviation angle and the stagger angle at the hub station. Similarly, we can do our calculation for say our tip region. So in line to what all we have discussed for the hub station, we will be opting same for the tip station. So the thing is, the logic will be my absolute velocity at the exit of my rotor 1 at the tip, that's what is equal to absolute velocity at the entry of my rotor 2 at the tip. and that's the reason my alpha 2 and alpha 3, that's what will be coming to be same. Okay, and remaining design methodology, that's what will be remaining same. So be careful here. In this case, the calculation for beta 3, that's what is mainly been based on what we say, what world component we are calculating. Okay, now when we are opting for our free vortex design concept, we can do our calculation for delta beta, we can do our calculation what we say in sense of relative velocity components, we can calculate what will be our de Holler's number. Okay, and based on our m parameter and the diffusion factor parameter, that's what can be calculated using the calculation of solidity and pitch. Here this diffusion factor near the tip region, that's what is coming to be 0.34 for rotor 2. Now these are the calculation for my camber angle, deviation angle, as well as for the stagger angle. Now compiling all this data, okay, so with the interest of time, I am not repeating the same words what all we have done. Since these slides will be available with you, just cross verify with the numbers. Okay, and this is what we will be making in sense of at different stations, say hub, mid and tip station. Okay, now this constants what we have calculated, it is minus 1.27. we have done our calculation for diffusion factor. You can see near the hub region I will be having diffusion factor to be large, near the tip region diffusion factor, that's what is coming to be lower. Okay, delta beta is also coming in the range of 24 degree at the hub and 7 degree near the tip region. Okay. Now this is what is representing the whole axial seat. It is preferred you just go through this lecture, then after you just cross verify with the numbers, try to make axial seat program and do modification and check with whether you are getting what all we are discussing with, and that's what will be building your confidence. Okay, now this is what we were discussing in sense of variation of different parameters, say diffusion factor, camber angle, de Holler's number. The question may arise in your mind, sir, for stage design you are discussing about degree of reaction. Here the degree of reaction term, that's what is not coming. Be careful, degree of reaction term, that's what is applicable when we are having rotor and stator combination, when we are talking about the stage. Okay, here we are having both the rotors, and that's the reason why degree of reaction terminology, that's what is not applicable for contra-rotating fan. There are some open literatures where people they are trying to opt for say degree of reaction derivation, but it seems fundamentally wrong, because degree of reaction terminology we are defining in sense of what is happening with rotor and what is happening with the stage. Okay, now we have done our calculation with assuming the deviation angle to be 4 degree even for rotor 2, and based on that we have done the calculation for the corrected camber as well as say corrected stagger, and this is what is coming out as a rotor 2 blade. Okay, now here in this case if we look at my twist for rotor 2 blade seems to be lower. When we are comparing here for our fundamental design approach, the twist that's what is coming to be slightly larger when we are comparing these two design approaches. Okay, now this is what is representing how my flow parameters, how my blade angles, diffusion factor, de Holler's factor, that's what is varying. We are more interested in sense of comparison. So here in this case if we look at this red color one, that's what is representing the fundamental design approach for delta beta, okay, for rotor 2. So here this is what is representing how my delta beta, that's what is varying near the hub region and near the tip region. if we look at carefully, my delta beta for the free vortex near the hub, that's what is coming to be larger compared to what all we are discussing for the fundamental design approach. Okay, this is what is representing how my say absolute flow angle, that's what is varying. And it is interestingly, we can see my alpha 4, that is nothing but the angle with which my flow, that's what is coming out from rotor 2 or my contra-rotating stage, that's what is having say angle in the range roughly say 11 or 12 degree when we are opting for fundamental approach. And when we are opting for the free vortex approach, this angle is coming to be large near the hub region. Okay, now this is what is representing how my delta beta, my de Holler's factor and diffusion factor, that's what is varying along the span. So finally, if we look at the two design approach or methodology what we have discussed, say fundamental design approach and free vortex design approach, if we are comparing the blade shapes, you can see here this is what is representing my rotor 1 blade. Okay, this is what is a view from one side, this is what is from the other side, and we can see carefully near the hub region for the free vortex concept we are having delta beta, that's what is coming to be large. That means I will be having higher turning of the flow, that's what is happening near the hub. And because of my free vortex concept, I will be having my blade to be highly twisted blade all the way from hub to say tip region. In line to that, when we are opting for say free design concept and say for fundamental design approach for say rotor 2, not much variation, that's what can be seen here. Okay, now this is what is all we need to discuss with. Mainly the variation, that's what is happening near the hub region, that's what is creating the design to be more challenging, both for rotor 1 as well as for rotor 2. Especially when we are discussing a low speed compressor design, the design for the hub or hub region, that's what is always a challenging task. As we have discussed earlier, this design methodology, that's what is say for this case we have assumed rotational speed for both the rotors to be same. You can go with variation of rotational speed. Maybe you can go with say higher rotational speed of rotor 1 or maybe higher rotational speed of rotor 2 compared to each other. Okay, that is possible. You can go with this. Okay, so many design possibilities what all we have for contra-rotating fan. Now in sense of having this to be applicable for many purposes, say for future eVTOL engines, say for future tunnel fans. Okay, so looking to all the applications, it seems like more focus or more design calculation or more development need to be done for the contra-rotating fan concept. So here we are stopping with, I'm sure now based on what all we have discussed about the design methodology for fundamental design or fundamental approach and free vortex design concept, you are able to design say low speed contra-rotating fan. Thank you very much for your kind attention. See you in the next lecture.